Well, I was going to say some words, but I think that you can start.
Okay, just let me start. Okay, thank you, Dr. Escobar. Hi, everyone. Good afternoon. My name is Xiangyu. I'm from Arizona State University. I'm happy to be here to present my work, our work, stableKanren, integrating stable model semantics with miniKanren. So kind of like building a new solver for the non-monotonic logic programming. This is the outline of my today's talk, including an introduction. Basically, give you some motivation about like why we want to build this kind of solvers, some background and the related work, because everything is in the title. You want to know what's stable model semantics and what's miniKanren that you can find out from the session 2. And the third session is about like our work. So like what's the stableKanren looks like. Lastly, I will close with some conclusion and the future work. Hopefully, can inspire more people joining to working with us. So the first part, introductions. So we all come to the PPDP because we love declarative programming. They basically allow the user to describe what you want, but you don't need to care about how to do it. Leave all the chores and the chaotics to us, to all the researchers and engineers at PPDP. That's the essence of the declarative programming, okay? So logic programming is one of the declarative programming paradigms, right? You're turning the unidirectional function into the bidirectional relations. So a logic programming solver treats the input program as data, creating an internal control unit. So you can see it separates out the control parts to us. So we need to figure out how to compute, how to optimize to produce the result as soon as possible. So still, this is the essential aspect of the declarative programming. Then Prolog, everyone hear about it. It's famous, notoriously good and bad, love, hate. It's an example language based on the unification and the resolution algorithms. So this is a very good example about the Prolog. The append, everyone learned from the Prolog 101, you will see, okay, for the append, we write down, we have the base case, when this is empty, we have unifying the as source and output, and then we have recursive cases. So the good things about this program is because like, okay, we can not only just use it as a solver, we can ask like what's the A or one append like to a list of 2 to 3, what we will get as a solver. It can also work as a checker. We can see, okay, if they produce the right result, can we prove it or not? And also like we can work as a prover. We leave X, Y as the variables, and it will ask you, like, give me all the proofs. Like you generate from empty list 1 to 3, blah, 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 to give you all the answers. So that's a good thing. But some researchers believe like, okay, functional language could be used for implementing such systems. That's why we have systems like miniKanren and the log Lisp have been developed over the years. So that's what the miniKanren looks like. So in miniKanren, I love to add everything with the O to the end to represent its relationship. So for the append in the functional language is the traditional function to append to list. That's it. So if you want to do the relation things, they call it appendo. So for the appendo, we can see the mapping. This is the Prolog versions, okay, base case to recursive cases, right? So in miniKanren, you have like the core miniKanren, it comes with the unification. You also have the cond, basically is doing the disjunctive parts, and you also have the fresh to introduce the new variables. So as we can see, so this is the direct mapping. Like for example, this is the append, and we give the input. This is the first input parameter, and second S and out. The base case when it's null, we unify 2 things together. And otherwise, when there is recursive cases, because in Prolog, we already done a lot of optimization there. So this is like what they call T is like a syntax sugar, but in miniKanren, you have to write it down by yourself. You break it down the list into 2 parts, head and tail. You introduce the 3 variables by yourself. And lastly, you combine the result into 1. Okay, so this is from the high level things. We're looking to, okay, what's the miniKanren version of the appendo you can use. So you can see it's exactly the same. So it's a miniKanren is a replicate the essence of a Prolog. They're using the macros to create a static search string connected through the continuations. So all these highlighted words is kind of important. We are going to invest into more details later. So that's why we probably want to dive into a little bit about underneath the hood of the miniKanren. Okay, what's behind the appendo? What's the equal sign, cond looks like underneath it? So first part is the functional programming and miniKanren. So for functional programming, we all know like the cons, it will create the list for us, right? It is like execute immediately, return a list to you. But here, like we introduce a thing called a lazy list, and eventually it can turn into the string. So it's just like, okay, we wrapped everything with lambda, because in functional programming, we love lambda. We wrap everything with lambda, everywhere is lambda. So as soon as we wrap the things with lambda, then the whole list becoming lazy. Why? Because you do the coder, you didn't get out the one immediately. You to return the function to you, you have to evaluate it again, so you get a one. So this whole lazy list things open up a new computation paradigm everyone probably heard about. It's called continuation passing style, the CPS. So for this kind of CPS, like, okay, we have the continuation. So in this case, we wrap everything in a lambda. This is the continuation for the counts. Counts is expecting some values, like in these examples, it may expecting for the one passing to you. And you can also expect all other things. Like, okay, keep a 2 to it, 3 to do it. So you can taste a little bit about like, okay, if we can use continuation and all these lazy strings, it kind of can do the non-deterministic search, right? So 0 after 0 maybe can be 1, can be 2, can be 3. So this is an advantage of the continuation. Everything it can be applied multiple times. That's how the miniKanren actually utilize these good things in functional programming. Oops. So we can start building it from the scratch by ourselves to using kind of this lambda and the lazy strings to achieve our goal. So on the right hand side is the traditional Prolog, what does it look like? On the left hand side is our ways of building the miniKanren. So in miniKanren, there's one function is very important called the go function. So go function is basically just a lambda. It takes in the substitution as an input and returns the extended substitution s after the computation. If the computation succeeds, we have the extended substitution set, right? If it fails, for example, there's a conflict in the substitution set, okay, we terminated the computation. That's the false in the logic programming. So in the first rule, it's very simple and easy. We do nothing. We just return s itself, right? Because for the p, x, and y, there's no other rules later. So now we add one thing, ax. So for p of xy, that is true if ax is true. For ax is true, you just unifying x with 1. So if we want to build our miniKanren versions, we just, okay, this is the continuation, right? This is the lazy things part. So the ax is waiting for some result coming from the substitution. We pass in here, we compute it, and it's done. Then to make it like a little bit complicated, okay, how about we add the b of y? So in this case, okay, ax run it first using s. You will return something like here is the extended substitution set, right? Then you passing into the by. Then by take all these things. We just continue the computation until all the go function we finished. Okay, so that's the very simple essential part of the miniKanren. This lambda get. That's how they created the special syntax notion to represent the internal go function, then maps the substitution s to all the sequence of 0 or more substitutions. So in this way, they kind of enforce the contract. Okay, there's no surprise. Make sure like the continuation will forming search strings. So we were doing a lot of modification on this lambda get in our stableKanren, and we will also build out the tons of macros to do the transformation. So here are some like benefits of using functional programming. I will not talk too much about it. So let's talk about the semantics. So the semantics, the miniKanren build is the monotonic under the monotonic reasoning is the minimum model semantics. Okay, because the resolution every time is the greedy, assume just one go is true. So that's why we will only collect the minimum sets of the true variables in there, true assignments in here. But in logical coding community, people start like thinking about what happens if we have a negation in the rules. So it turns in the logic program into a normal logic programs. So in this case, we achieve the non-monotonic reasoning. So with negation, it will allow the conflict in your knowledge base. So you can do belief revision. So and your whole knowledge base will not collapse if some bad things happen. So this is one example about a two-persons game. We try to describe in the winning position defined as there is a move that will make it so the opponent has no move. So in this case, for example, if I'm at a C, is the winning position, because if I move from C to D, my opponent, he has nowhere to move. So he lost, I win, right? So to find the semantics for that kind of the normal program has a long history in logic programming community. That's why we are looking to okay, what's the normal logic programming looks like, and what's the stable model semantics looks like. So for the normal logic programming, a normal program is simply just add one not into the atom in the definite program. So each one of this is turned into the literal. That's the only thing added into here. Oops, okay. Then the semantics in this kind of normal logic program, we can categorize based on the relationship between the loop and the negation. So the loop is defined by unfounded set. Is that in a normal program that it can help correspond? The unfounded set means the atoms inside the unfounded set are only cyclically supporting each other. So it's like A, B, C, D, and it's kind of okay. There's no external support. Then we can considering these two combination of the negation and the loops. So as some category, so in a very early stage, we do not allow any loops inside. We can do negation. That's where is the clock's negation as failure comes into play. Okay, then later we can say, okay, we can have some loops. We can also have a negation, but these two things does not mix together. If you use the negation should not show up in the loop. So for this stratified program, Alan Van Gelder defined the well-founded semantics. It's for this purpose. Then eventually we have the stable model semantics for no restriction. So from the high perspective, we can tell stable model semantics handles the negation and the loops. Then we will see how it handles from the high-level declarative semantics levels. And we want to achieve handle the negation and loops in our solvers. So this is our goal. Then what is the stable model semantics? So stable model semantics usually have three steps. The first step is creating a propositional image. So you basically a grounding. You remove all the variables in your logic program, turning the predicate form into the propositional form. Then later we enumerated all the possible interpretations, right? Because once it turns into the propositional form, we know they have n atoms. So we will have 2 to the power of n interpretation of that. So the second step is okay, they will use the interpretation to create the things called the readout program of the propositional image. After you create that, the third step is okay, now it can be run using the traditional Prolog to obtain the minimum model of the readout program. And the last step is you need to check if these two models are equal. In the beginning, the interpretation you choose is the same as the minimum model you got eventually. If these two things matched, then we say M is the stable model of P. Okay. So here's one very simple examples. We have one program, only have two rules, P12, QX is true of the PXY and the not QY. So first things, like I say, we'll create a propositional image of that. So after the steps, we will have 1, 2, 3. We will have 3 atoms, right? So in total, we will get 2 to the power 3 interpretations. So here I just only list out 2 of the 8 to show you about okay, once we have the propositional image, how we can produce the readout, and why the left-hand side is not the stable model of the original program, while on the right-hand side is the original is the stable model of the original program. Okay, so from at this point we can see stable model semantics actually is a generalization of the minimum model semantics. Okay, it still have some minimum model things in there, right? If from the declarative, why is it stuck there? Oh, okay, good. Yeah, so from the high level, you can tell there's one step is computing the model of the readout program is the minimum model. That's why we say, like, okay, stable model actually is a generalization of the minimum models. And we also want to use like this nice property in the resolution. We want to keep that in our stableKanren, we will see later. And also we found out like, okay, solvers implementation, like kind of like shifting from the top-down resolution and the unification to the bottom-up grounding and the constraint propagation. So the later one, it achieved a very good solving performance, but it created a lot of like heavy memory footprints. And at some point, the people believe like maybe the top-down solving is impossible. But here, like we try to show, okay, actually we can do that. We try to go back to the top-down approach with the resolution and unification. So also, like there's no logic programming server implemented, normal logic programming server implemented in the functional language. So we want to do that. So we want to have our stableKanren to bridge kind of these gaps. So some construct we also realize that like we have seen a lot about the macros and the continuations can help us to build kind of this kind of like normal logic solvers. And also like miniKanren has a very nice things. It's like, okay, everything there you can modify, the asset is open access to you. You can change it without any headache. We will show you how to do that in the later parts. It's very straightforward. So this is the relationship between the two systems. So for example, like we said, miniKanren is the replicate of the Prolog, and we will try to extend it with the stable model semantics. We have stableKanren, and in the non-functional programming implementation parts, we have ASP, Klingo, SASP. So this is the equivalent to our stableKanrens. So quick recap, miniKanren replicate the essence of Prolog through the macro and the continuation, okay? Then stable model semantics, it defines a way to handle the negation and the loop. This is kind of like we try to do. We use the macro and the continuation to handle the negation and the loop as well. And the miniKanren allow us to easy access and the modification of the underlying unification and the resolution. So we also like have a better understanding of the stable model semantics. I found the property of the stable model semantics. We discover a way to extend the traditional unification and resolution to support this stable model semantics. All right, and how we do that? So as I have mentioned, like, okay, there is one property, very nice property in the stable model semantics. It's like, okay, let pi be the propositional program and m be an interpretation. M is a stable model of pi if m is the minimum model of the readout pi m. So from here, we kind of try to see, okay, if we can find the minimum model and the readout program at the same time, like simultaneously. So previously, in the declarative version, you know they have multiple steps. First, we create a propositional image, we get the readout, then we solve, we get it. But why we need to do that? If we can do it like simultaneously, we get both things at the end. So that's the stable model of the original programs, right? So therefore, like the key idea in our of the reader is like, okay, you try to remove the loops and the negation. So in our algorithm, like we have the negative goals, you work as a checker and a remover, while the positive goal as the generator. And back to the resolution and the unification. As I have mentioned, resolution in the beginning only has one rule, selecting one goal. We assume is true. That's the only task it's doing. And in our stableKanren, we will grant 4 more rules to the resolution, as we mentioned here. And same thing like for unification, it plays two rules. One is like, okay, we try to unify the variables with some certain values, and also produce the truth values for the goals. But for the unification, we only wanted to produce the truth value for the negated versions. So under the negation, we don't want the unification to assign the values. So that's a very big assumption about the variable safety I will talk about in the next slides. Then for the resolution, as we have mentioned, it has to taking care of the loop, and it also needs to distribute the negation, like from very high level, complex, compound code, all the way down into the unification level. Because at unification level, we handle the negation there. Okay. Then similarly for like, okay, for the variables in there, we have a domain we need to handle, because in stable model semantics declarative way, during the grounding, you already remove all the variables, but we have to handle the variables. You will have some domain values we need to compute, and we need to run our solvers on that computed domain for the further computation. And then lastly, because like, okay, this stable model semantics is the NP-hard problems, the partial result we get is not the global result because there's no optimal substructure there. So whatever partial result we get, we still need to get the resolution to continuing execute until we get the whole result. So that's the kind of a system overview of our stableKanren. So we have the macro and the transformer. It will create a complement program for the negative goals. And we combine the negative goal with the original goal together with some like for all values, like I have mentioned. We need to check the variables, the domain, and compute everything there. With some negation handler, loop detection, partial result set, the whole thing is becoming our stableKanrens. All right, this is the variable safety we talk about. We need to make sure every time before we call in the negation, all the variables are assigned, or kind of like we can say it's grounded. One way can do that is like, okay, during some compilation time, we can do some rule rewriting to make sure all the positive goal comes before the negative goal. But you also have some other issues, like during runtime, maybe when we are evaluating the negation, the negative goal, the value is still not bound. We may try to postpone or maybe suspend this computation later until this value get bounded. So this is still under our current work right now. So but in this paper, we have an assumption like, okay, when we try to handle negation, it is already assigned, okay? So we one go, two sides. We don't want the user like, okay, you write down the positive version of the program, and you also need to give us the negation parts. This is not a declarative way, right? We want the user to give us the original positive programming, then we do the automatic compilation for you. So we kind of want to combine the negative goal and the positive goal together into this one wrapper. So that's why like we have a thing called a defino. Later we will see. But before that, we have some like I said, we heavily modified this like lambda g-add, the goal function. We need to introduce kind of a negation counter to count like how many negation we intercount. If the negation of the negation, double negation means positive, right? This is kind of the purpose of the negation counter. Then we also need to have like call frame stacks, CFS to make sure that we encounter the loop. So this is kind of the new things we introduced to this lambda g-add to add two new things into the continuation. And we have one more new macro, noto. It's just a not operator, but because the not, this keyword is being taken in the scheme language, so we call it noto. So in noto, it's very simple. You just simply add one every time we see a noto. Then this is the defino we mentioned. Like, okay, Clark already want us to combine the two goals into one. So we have a defino. It will based on the negation counter. If it is the even number, means like we are handling the positive goals. So we just do whatever the expression exp the user give to us. Otherwise, if the odds is the negative goals, then we need to handle the complement form. Is the negated form. Okay. Then how to implement this complement, we'll leave as future work. Here, just give you a higher glance about the defino. So the unification will give one more role to produce the truth value for the negative goals, right? So this is how what I said. miniKanren is very easy to modify. This is all the original unification algorithm they provided there. So I want to add one more thing to it. Oh, okay, if this is the positive goal, you do whatever you did before. But once we have a negative goal, how about we do like this way? Okay, and as I mentioned, because the variable safety issues, we assume everything is safe here, so we can safely do this right now. Then later we need to ask the resolution, okay, go to distribute it, all the negation to all the way to the base level, unification levels. So to distribute it under the propositional form is relatively easy because each atoms, they're independent with each others. So we can use the De Morgan rules directly. So here is like showing like how to write the De Morgan's rule just as the macro, one-to-one mapping. This is what you think, and then you write it, this is what you got. I will leave this to you to read later, but the key idea is like, okay, using the macro to write down all the, no matter it's the De Morgan's rule, or the later we introduce our own transformation. It's very simple, concise, and easy. We really love this. Hopefully you guys can also appreciate this kind of nice things. Then we found out, okay, De Morgan's rule doesn't apply when there's a predicate rules, because each sub-goal, or maybe the variables, they are kind of dependent to each other. They are not independent anymore. So we need to come up with our own transformation. How much time? 5 minutes? Okay. So I will leave all the detail about like how to come up with this transformation to you guys to read about it. But once we come up with this transformation, we want to write the transformer or the macro. It's also like very straightforward. And what else? Yeah. Then maybe the third row, the resolution. This is the second one. First one, we already distributed the negation all the way to the base case. Then the second one, handle the variables. Right, so for the variables, previously resolution is like, okay, there exists one. But once we have a negation to that, not exist means like for all. So for this kind for all, we need to change the execution curves of the resolution, right? Previously, we only find one answer, okay, that's good. But right now, we need to let the resolution to go through all the values. And the resolution also need to figure out what's all the values about. So this is all these sessions about like how to compute the domain values, how to iterate through all the values. Then we come back. Then third thing is the loops. So in the normal program, we have positive rules, we have negative rules, and further we can categorize into all the negative rules and even negative rules. We can also assign the corresponding semantics to it based on the stable model semantics. So also like can implement it in the scheme, stableKanren. And then lastly, like we need to go from the partial resolution to the global resolution. It's all the 4 rows we granted to the resolution. And once we have it, at this point, we extended the resolution and the unification with stable model semantics in miniKanren. Then we get a stableKanren. And so as the future work, we want to support the constraint rules and the choice rules. Also want to solve the infinity Hilbert model and maybe add like inequality constraint, a lot of things in there. And more importantly, we want to apply the bottom-up, state-of-the-art, conflict-driven local learning CDNL algorithm to the stableKanren as well. Okay, thank you guys for your time. Thank you so much.
Questions?
So thank you for the talk. What's the performance like of your stableKanren compared to like the ASP solvers?
Yeah, I did a small comparison with the SASP on the n-queens problem. It already like 3,000 times, sometimes like 10,000 times faster than that. And I want to add the constraint rules into there so I can do some comparison with Klingo, because the Klingo, they're using the CDNL algorithm, so that's the state of the art. Yeah, but so far we are looking kind of good with the top-down solver domain. So yeah, thank you.
Thank you. This was a very interesting workshop. At the start of this talk, you made a little bit of a introduction of what we can consider declarative. And I've always been very curious. I've tried to understand where is the boundary, So, like, is the new Java streams declarative enough to be considered declarative programming? Or is the general feel of the people in the workshop that is still way too, conventional, I don't know how to say, to be called declarative programming? Well, what do we think?
I think there's one very interesting example. For example, LaTeX or maybe HTML, everyone use it, but some people hate it because it's just not follow what you want. And in that case, the user may want to say, okay, I wanted like a word, I can adjust the picture by myself, right? So this kind of boundary, like very blurred, we may have some fallback situation. So when user is not happy about our solver's result, we will let the user say, okay, go define your own way to solve it. Go define UDF, user defined function, right? So miniKanren also can support you can define the customized function to achieve your goal. So the boundaries are very blurred.
Yeah, that's in my research, sometimes I need to make some comparison, some discussion. So I have to say, this is clearly declared, and should I say that? This is more declarative than that. I always have to make those very indirect sentences because it's really hard to understand where is that you can meaningfully say this is declarative.
Yes. Yes.
Yeah. Anyway, sorry.
I agree.
Any questions? Yeah, well, it's late already.
Oh,
No. But I was also going to ask whether you compare with other Prolog implementation. I mean, you already answered that question, right?
Yes.
Because well, so from one side, so you see, so on one side, it seems that you can get really a performance improvement, okay, because of the way, right?
Yeah.
But some other features look like they are going to be very slow. So this is so my question was going to be also that one, okay? But what you said is that you just try the Queen's example,
and Queen's,
only that. Okay.
yeah.
Okay. Because in Prolog, you see a lot of things really have to do with whether you do this generate and test or the test and generate.
Yes.
So I mean, Prolog is quite complex. So
yes.
probably I think that what you really need is some more realistic comparison of
Yeah, I agree with that because this step is just a framework of the first steps, and later a lot of optimizations we want to introduce into this kind of functional style framework, and then you also need to change a lot of mindset. So in the Prolog, maybe you implement it in the C or C++ way. You cannot use the variable assignment in the functional programming. Like this kind of thing, you need to transit to like the list to the string transition. Yeah. So once we achieve that, maybe the future of the Prolog looks much brighter.
and the very last comment, I was missing. Well, I had to do some things. Sorry, maybe I lost some parts of your talk, but I was missing the purpose of your talk, and you said that very last. So in reality, you want to do this to do the close learning thing, right?
Mm-hmm.
Okay.
Yeah.
Okay, so thank you very much.
Thank you. Thank you.
Well, so